In this video, I will explain how to use the event detection feature of MATLAB. The discussion will follow closely that found in the MATLAB book, Differential Equations with MATLAB, abbreviated here DOOM, on pages 127 and 128. It will include an illustrative example, very close to the example in the book, of a first-order equation, and then I will augment the discussion with a second-order example as well. A more sophisticated example involving systems of equations can be found in a later video that discusses the so-called deal command. Anyway, as it says in DOOM, sometimes the main question of interest in a problem that is modeled by a differential equation is when a specific event occurs. For example, in a falling ball problem, when does the ball hit the ground? We will show how to augment the ODE45 command with a procedure that enables us to answer such a question rather precisely. So let's begin. First we'll clear all the variables, close any open graphs, and the format long sets the default number of significant digits in MATLAB to 16. Now, for illustrative purposes, here's the problem we're going to look at. It's a first-order equation, y prime equal t over y plus t, y0 equal 1. And you should note that this differs somewhat from the example in the DOOM book on page 127, in which the denominator there is just y. I did this to render the problem unsolvable by dsolve. And let's check that here. So I'm going to try to solve this differential equation by dsolve. I run it. And it's thinking a little bit. You can see that from the circle, and it's finished. So let's see what happened. Nope, MATLAB couldn't solve it, and it admits as such. Okay, so we have to work with a numerical solver. We use, of course, ODE45, our numerical solver in this course. And let's suppose that the question that we have in mind is, what's the moment at which the solution function reaches the height 1.5? Okay, so let's graph the solution to the IVP using ODE45 on the interval 0, 3. So I clear the variables because I set y and t to be symbolic up here, so I want to do away with that. Here's my syntax for ODE45. It's 1 at y equals 0, and I'm solving on the interval 0, 3. So let's run it, and there's the graph. It looks like an increasing function, and it gets to y equal 1.5, I don't know, around 1.3, 1.4, not clear. We want to determine that value as precisely as we can. So the way to do that, to obtain a more accurate answer, that is the moment at which y is 1.5, which we've estimated is about t equal 1.4, you have to create a so-called auxiliary m file, which we are going to call EventDetection.m, that describes to ODE45 the event that you want to detect. Among other things, this m file must specify a quantity that changes sign when the event occurs. Here is an appropriate event m file. It's called EventFunc, and I've had MATLAB type it out for us. So if we run the section, then the file will be in the MATLAB, window. Here it is. That's not okay. So EventFunc here. It's a function of t and y. It has 3 outputs: event, stop, and dir. And I have to explain what these are. You can see the 1.5 over here. I'll explain those in a minute. But let's go back. And before we do that explanation, let's show you how to produce the desired output by running the following commands. So here are 3 commands that will do the job for us. Before I evaluate the cell, let's explain it. So the first 3 inputs to ODE45 right here are exactly as before. Then it has a 4th input called options, which takes the output of ODE set and tells ODE45 to cough up some information. The 3rd and 4th outputs over here are the values of t and y at the moment that the event occurs. The first two outputs here are just the usual vectors, these first two, containing the vectors containing the intermediate values of t and y that are computed by ODE 45, and of course those are what are used to draw the plot. Okay, let's evaluate this and explain how the event detection file eventfunc.m, t missing here, works. So let's evaluate this cell. And if we look in the MATLAB window, there's the answer. So y is 1.5 when t is 1.4616, etc. So there's an approximation to 16 significant digits for the moment at which the event occurs when the height y of the solution reaches 1.5. Okay, the next step is to see how the event file works. We turned on the event detection by including a fourth argument, ODE 45, as I said, options. It contains the output of ODE set, and that output has three elements. The first, which we called event, actually I've got that file right here, so there it is again. There's the event file, the event detection file. Event is y minus 1.5. That's the quantity that changes sign when y is 1.5. Okay, let's now go back to the editor. To the event function. Okay, the second output, which we called stop, must be 1 if you want ODE 45 to stop solving the differential equation once the event happens, or 0 if you want it to keep going, and we had stop equal 1. There it is. So, in fact, ODE 45 stops working when the event occurs. Okay, back to the event detection. And finally, the third one, which we call dir, it must be 1 if you want the event only to occur when the event itself changes from negative to positive, a -1 for positive to negative, a 0 for either direction. What did we set it equal to? We had it equal to 0, so either direction. It would have worked with 1 as well, because the function is increasing, so it's changing from negative to positive. If we had put dir equal -1, it would not have detected the event. Okay, for illustrative purposes, suppose instead you had been asked when the solution reached 2 rather than 1.5. What would you have to do? You'd have to go back and change the event file. So change 1.5 to 2, save it, and now let's run the commands again. So I'll go back up here and run this cell, and if we do that and look in the MATLAB window, it happens at 2.415, etc. This is when t equals that, that's when y equals 2. Obviously, just by altering the event file, you can set your parameters any way that you like. All right, let's return to the editor window and continue on. And now let's look at event detection for a second order equation. So I will consider here a damped rigid pendulum governed by the second order equation, y double prime plus 1/10 y prime plus sine y equals 0. This is the usual damped pendulum equation. The damping coefficient is 0.1. Y double prime plus sine y equals 0 is the usual equation. An undamped pendulum, this one is damped. Let's assume that it starts out at rest, so y of 0 equals 0, and with an initial angular velocity of 1 radian per second. So that's not hard enough to get the pendulum to go over the top. So what will happen, it will swing to the right and then come back to the left, and it will simply rotate back and forth with decreasing amplitude. The question I want to consider is, at what time does the pendulum first pass back through the equilibrium position? So when is y equals 0 again. For which first time? Okay, I'm going to follow the same scheme as above. I'll first graph to get an approximate value, then apply the event detection method. And as explained in Doom, we must express the second order equation as a first order system in order to apply ODE 45. So now I've called my function g instead of f. Y1 is just y, y2 is y prime. So the system now is y1 prime equal y2, or y prime equal y prime. And then the second equation is the second derivative is minus 0.1 y prime minus the sine of y. So there's my second order equation expressed as a system. I apply ODE 45. I solve on the interval 0, 3. Y of 0 is 0. Y prime of 0 is 1. And let's see what comes out. I'm only going to plot the first variable here. So only the position. If we run it, there it is. So the angle increases, almost gets to 1, and then decreases, and it looks like I didn't run the model long enough because I didn't get back to 0. Right? So I only got back to around 0.25, so I need to run the model a little longer. So here's the same set of instructions, but instead of going from 0 to 3, I go from 0 to 4. Let's run it. And this time I did run it long enough, it came back down, and I've obviously gone through 0. Where have I gone through 0? I don't know, about 3.4, 3.3, a little hard to see. So again, we will use event detection to get a much more accurate depiction or calculation of for which value of t theta is 0. Okay, so I'm going to use a slightly different event function. This one I called event func2, and here I'm typing it, but instead let's just look at it. Here it is. Very similar to before, but the only thing that's different is the event. It's y1 minus 0. Notice this time I put dir equal minus 1 because it's going from positive to negative this time rather than from negative to positive. And then let's go back to the in the editor, event detection. So the setup is exactly the same as before. I'm using the function g, solving from 0 to 4. I'm using event function 2 rather than the first one. And if we run it, what happens in the MATLAB window, we see that this is the value. It occurs at a time equal 3.337, etc. That's when y is back to 0. And what's this additional value? That's theta prime, or y prime. So that tells me that the velocity is negative, right? It's coming back to the origin, and it's approximately 0.85. Started out with 1. So the pendulum is swinging less rapidly than it was when it started out, which is exactly what you expect since it's a damped system. Okay, so that's how you use event detection to compute when specific events occur using ODE 45.